the first speaker in the afternoon. He's Michael Polyak, and he's going to talk about enumerative geometry and finite type invariants. Thank you.
So it's a pleasure to give a talk here. Actually, you see, it's not actually the Technion, it's Technion and CINVESTAV. But CINVESTAV is too long, so it wouldn't fit here. So I was fighting with it for a while and then decided, but you should know that it's Technion and CINVESTAV. Now, I'll keep presentation on a very, very basic level, because I was, when I was a postdoc, I was always jealous of all these, guys who would give a talk about philosophy and something without proving any theorems. So here's my opportunity to do that. So what I'll try to do is to pass two ideas back, basically, and the first is that real enumerative geometry is very intimately related to a notion of finite type invariants. This is the first one. And the second punchline is how do you produce certain enumerative invariants, and these the suitable technique and very powerful is certain intersections in homology. Basically, I'll explain this in the second part. So first of all, let me just very briefly pass over the whole setup. So in complex geometry, and especially algebraic geometry, all objects are very rigid. Both because some of them are algebraic, and then of course you cannot bend them or do anything, they're extremely rigid, but also because of the nature of complex geometry, because the moment you fix some function in there, in a small neighborhood of a point, this is it. You cannot change anything. On the other hand, in smooth topology, all objects are extremely soft and flexible. You can just take some little piece of a curve and bend it the way you like. So what I would like to play with is some kind of algebraic enumerative geometry mostly, and such algebraic objects, they do remain rigid. Right? If you have a line, it's a line. You cannot do anything with that. But on the other hand, I would also like to work with some smooth objects. So I'll work with both types of these objects simultaneously. You will see how does it work. And the second important thing about the real geometry is that, well, in complex geometry, you just count things naively, right, without any signs, or more correctly to say, it's always with positive signs, right? However, as we all know, in real topology, we should count things all with signs, whatever it is. Say, degree of a map, you should count it every pre-image with a sign, which is a local degree, etc., etc. Right? So we should count in all these enumerative real problems things with signs, right? So the simplest case of enumerative problems which I would like to consider is just looking at the space of all immersions of a circle into the plane, and I will work mostly with generic immersions. What is generic will depend on the problem very seriously. So I will just sloppily say generic and just look at these pictures, and these will be non-generic, right, by several different possible reasons. So here there's an intersection point of high multiplicity, here's a self-tangency, and here this piece is just totally straight, or at least I tried to draw it totally straight, right, which is certainly in some sense non-generic, but it will strongly depend on the problem. So now let me start with a very kind of simple baby example of a thing like, if I take a point in a direction, there's one line passing through. Right? Of course, yeah, good. Now, similar tangency problem, which is also very simple, is that I would like to count not just lines passing through a point, but rather lines tangent to a certain immersed curve. So I take a smooth object, immersed curve in this case, and I just count lines which are tangent. And so this was supposed to be a tangency point, and this also. Sorry for that. Now, the important thing is that, of course, as I stated, counting them doesn't make sense because this number under any small deformation may very easily jump. However, if we try to count these lines with signs, then immediately we get a problem which is pretty reasonable. In particular, of course, there's a simple Morse type move where I take a small fragment of my curve and I introduce here two critical points like this. Then, so I got a pair of new tangent lines. So if I want the result to be invariant, then they better be counted with opposite signs. And then immediately, of course, we come to the simple rule of signs is that depending on kind of the local behavior of a curve near this tangency point, I assign either positive or negative sign to this tangency, right? And then the result is indeed very good. It is totally invariant. It's just twice the rotation number of the curve. So it is preserved in the class of immersions. And here's some simple examples. So this is a curve of rotation number 0. This is rotation number 1. I rotate once against counterclockwise, and here the rotation number is 2. This is actually the invariant for immersions. Right? So if I'm given an immersed curve, then I can deform it into any other if rotation number allows me to do that by homotopy. Now, so let's go for something less trivial, because this number is the simplest and it is preserved very well. However, now if we want to count lines which will kind of belong to both problems at the same time, so it will pass through some point and be tangent to a curve, right? So if I will count them with the same signs, then the result will, however, be dependent on the relative position of a point and the curve. So if the curve is not allowed to move through the curve, right? So if I just take the immersions of the circle in the punctured plane, then there it is invariant under homotopies. However, if I just push the point through my curve, then the number jumps, right? So here there are 4 tangent lines, here there are only 2, here they all disappear. So this is a standard simple baby example of such an enumerative real problem where some new things happen relative to the complex situation. While in complex cases, such enumerative problems always gave me a number which was well defined and independent on any relative positions or on anything else. Here things do depend on the position, however they're well controlled. These 4, 2 and 0 are very easy to understand, and in fact you can just understand very easily what happens when my point passes through this smooth curve. Well, if I start with this base point very far from the curve, then it's the same more or less problem as it was before. I would get just twice the rotation number, because if I take p to infinity, then I just count the parallel lines, right? However, if I push it through the curve, then I earn +2 every time when I push it in one of these directions, just as indicated here. So, while it is not invariant, the compensating term, this which is called the index of a point relative to the curve is very easy to describe and to find. Right? So these kind of real problems, they don't give you one number. It's actually a locally constant function. It depends on something, but its behavior is very well controlled. So this is very typical for such real enumerative problems, right? So, so here we are done more or less with these baby things. So let's go a little bit up, still staying kind of reasonable and simple. So if I would just like to count, say, double tangents. Now this is still a very similar problem to the previous ones. I can count these things, of course, again, with some signs, otherwise it would just change under some small local deformations. Now the moment I do count these double tangents with signs, the result is very nice. It still jumps. It jumps actually when these two curves slightly move one relative to the other, and when they pass tangency point, when just one is pushed through the other, then I earn two, or two local tangents disappear, or this way or this way, right? Now the jump is differs by sign, because these are the signs with which I count these double tangents. So again, the number of such double tangents, while it changes in a very well controlled way, and the result is up to a normalization, something which is known as J plus and J minus invariants, introduced by Arnold in the 90s. So it's something which just jumps under passage of such a tangency, right? So of course, so far it was really way too simple. So first of all, instead of counting lines, we can go up with similar algebraic problems, but just count high degree curves. Or we can go up in the dimension of the ambient space and just count some hyperplanes in some high dimensional plane spaces, which would be passage tangency problems or whatever. However, I actually don't even have to stay with some algebraic objects. The important thing about lines, say, which would be parallel to something, or go to fixed direction or something else, or passing through a point, is actually not that these are algebraic curves of degree 1. Rather, these are just certain families of some curves which behave very nicely in some sense. So kind of well-controlled families of objects. So instead, if I would take, say, and consider triangles which are equilateral, and I fix some direction of a side of one of the three sides of this triangle, and I can try to count such triangles so that all three vertices would lie on an inverse plane curve. Right? So while triangles are obviously non-algebraic objects, it's still a very nice family. It's a three-parametric family, which really behaves nicely in some sense. Or I could look at points, so that these are triples of points, so that all three lie on one line which is parallel on the say, to the x-axis, and the distances between pairs of these points are the same. And then it turns out that, again, if I count these objects with some signs, I don't tell you at this particular moment how to define signs. It will become later very clear. Then I recover the other Arnold invariants, so-called strangeness of planar curves, which already jumps on the passage of a triple point of an inversion. Right now, so let me just give you some example, which will be already much less trivial, counting conics, real conics, and so what I want to illustrate now is that if I have a certain way to count things with signs, with certain appropriate signs, and to get some nicely behaved function which would be locally at least constant, just the knowledge of the fact that I can do this somehow already can give me quite non-trivial results. So let's see. So I would like to talk about conics which are tangent, in general case, which are tangent to 5 ovals. Ovals just some, so just take it as embedded curves. Okay, so take 5 embedded curves, which are called ovals, and I look at all conics which would be tangent to them. Now, as long as my conic is irreducible, this is a reasonable thing. It can happen, actually. There are such conics which are tangent to 5 ovals. However, if I look at only reducible conics, so these are just cross of 2 lines. Right? So if I look at a cross of 2 lines, there's absolutely no chance that such a cross would be tangent to 5 ovals at a time. So I will be sloppy here, and I will say that a degenerate conic, so a cross of 2 lines, touches all 5 ovals, if in fact it is tangent just to 4 out of 5. Kind of the best possible situation. So now I would like to count such conics tangent to 5 ovals, and I would like to count both reducible and irreducible conics. Right? So now, theorem of Felchinger actually states that if you count correctly, so again with certain signs which Felchinger had to introduce, then there are at least 272 real conics which touch such generic non-nested ovals, and if the ovals are convex, then at least 32 of these conics are non-degenerate. So this is quite a tough theorem. It's a corollary of Felchinger's machinery, which is highly non-trivial. But in fact, we can just give an elementary proof. Let me just present you a half proof, which is already okay. So let me just generalize this statement. Instead of conics touching ovals, I will talk about conics touching 5 immersed curves. So instead of embedded curves, I'll allow immersed curve. And then let's see these numbers, 272 and 32. Okay. Now, what is known, the only thing which I need from algebraic geometry at this point is quite a well-known statement in classical algebraic geometry that through 5 generic points on a plane there passes exactly 1 irreducible point. Okay. This is the only thing which I'm claiming now. Okay, good. So let me just take 5 points, pass an irreducible conic through them. How can I use it for my problem? Well, let me just take one of these points and just blow it up slightly into a small circle centered in this 5th point. Now, it's quite obvious that what will happen is that instead of this one curve kind of conic passing through the center of this little circle, there will be pair of conics passing still through these 4 points, and which will be tangent to my small circle. Right? This is not a big deal. It's just a small deformation. There will be kind of 2 differ from which side do they touch this little circle. Okay. So now let me blow up each one of the 5 points. Now, if I blow each one of the 5 points, kind of I pass from a point to a small circle there, then from one point I got kind of 2 possible tangencies from the inside in some sense and from the outside, whatever this means. Then there are, since there are 5 such points, there are at least 32 kind of, right, such irreducible conics touching all these 5 little circles. Okay, good. Now, this was about irreducible conics. Let's count reducible conics. So, reducible conic is just a cross of two lines. Now, a cross of two lines should touch 4 out of 5 ovals, right? So one of the pair of lines touches a pair of ovals, the other line touches another pair of ovals. How many ways do I have to pick 2 pairs of these 5 circles? Well, obviously 3 times 5, right? Okay, now the moment I fixed such 2 pairs of circles, there are 4 tangent lines to each pair, right? Kind of depending on from which side of the person. So therefore, there are 3 times 5 times 4 times 4 reducible conics touching these little circles. And I still work with these totally round, smallish circles of, say, radius epsilon. This gives me 240, right? Now 240 and 32 are both nice numbers. Why? Because they together give me exactly these 272 of Felchinger. Now, of course, so we got it only in one case when I just blown up these points into these tiny round circles. But of course, so the whole assumption is that that the number of conics, if we define it appropriately and count them with certain signs, then it should be invariant, right? So if so, then I could just deform these circles into any other ovals. Now, why the number can grow? Why does he say that it's at least 272? It's because, you know, if it's not convex, then there are these little kind of critical points, and there will be more tangents than needed. Okay, so kind of this way, if we know how to define things and count them correctly with signs, then we can get these numbers very nicely and easily. So, the main things are, so first of all, I didn't tell you how to introduce these signs. Say Felchinger, how did he introduce these signs? So how is it possible to construct such invariants? And of course I would like it to do not just in one problem, but in somewhat systematic manner. And finally, we know that these invariants, they do jump. They are locally invariant. However, globally they jump. They depend on something. How can we identify them? How do we know when do they jump? So the second question is somewhat simpler, and we can answer it much faster. And the whole point is that all these invariants, if we construct them, then all these algebraic passage tangency problem invariants, they are of something which is called a finite type. I will explain it below. And in particular, if we count, say, a rational curve of some fixed degree d, then these finite type invariants, they have a certain also notion of degree. And this degree of a finite type invariant is at most 3d minus 1. Now, what are these finite type invariants? Finite type invariants, so this example which I gave before, it was a function which jumps, let's say, 4 to 0 in a certain well-controlled way. Now, so these are in some sense polynomial invariants, and they're defined for a wide variety of objects. And in fact, the person who first, it seems, was the first to define these things was kind of a slightly unusual definition of Fréchet, which he gave for polynomial function. Right, so we are used to the standard definition of a polynomial function when we say, well, it's a function such that blah blah blah, its nth plus first derivative vanishes. It's a bad definition because it cannot be generalized. It's kind of very specific for spaces which we like in analysis. Fréchet was interested in some more general setup. So here the point is that the only thing which I need here from analysis is that I look at all functions which are at least C0. Right? So some kind of, this is the only assumption which I need from a function. Such a function is called a polynomial, and it gives you a usual notion of a polynomial if whenever I take its values at some 2 in power n points, which are kind of, these are discrete derivatives, if you wish. I take a point and I slightly shift it to the left and to the right in different directions in some kind of nice way. And I add them up with certain signs. If it always adds up to 0, this is a polynomial function. So just think a simple problem to tease you is, what is a linear function? Just check this definition in degree 1. Right? So what does it mean that it's degree 1? Right? So a linear function. But it's less than 2. Right? So you should think about n being 2. All right. So this kind of definition works also in topology, and you can do it in the following way. So these little kind of discrete derivatives are the following. You just take, for example, for curves, for immersed curves, it's very simple. Just take a curve which would have n non-generic fragments. Here is the intersection point of high valence, and here is a self-tangency. And for each one of them, I pick up, arbitrarily in a sense, 2 different resolutions. Right? So I slightly deform them into different ways. And again, in an arbitrary fashion, I say one of them I call a negative resolution, one of them positive resolution. Ad hoc. Just take this as is. Right? Now, what is good is that now I got, the moment I fixed a pair of resolutions for each fragment, there were such n non-degenerate fragments, then I earn 2 in power n generic plane curves, right? Where I resolved all of these in one way or another. Now, if I have a function which is defined already on generic curves, I can take its value on each one of these and then add them up with signs. Now, if for any initial data, that is, the initial curve with these fragments and a pair of resolutions for each one, if it always adds up to 0, then it's called a finite type invariant of degree less than. Now, so here's again back. Let's go back to this example of double tangents. So let me prove that if I manage to count these double tangents with some signs, so suppose that they have some rule of signs, and then I manage to count them so that the total number of these double tangents is an invariant. So I claim that then this will be a finite type invariant of degree less than 3. Okay, now, so I just check it against my definition of this finite type invariant of a certain degree. So I should pick up an immersed curve with what? So if I'm interested to prove something of degree less than 3, then I pick something with exactly 3 non-generic fragments. I fix a pair of resolutions for each one of them, right? So I do change these things in just tiny, smallish balls. And I assume that already these balls do not lie on one line. That's an assumption. So the claim is that if I add up the values of my function, the value of my function is summation of the number of double tangents, right? Total number of double tangents over all these generic curves, then I claim that the total will be 0, just because of these rules of signs. Now, why is that? Well, just because if I make certain resolutions in, say, 3 fragments, right? So 1, 2, 3. then because these fragments are very small and then do not lie on one line, so double tangents are straight lines, right? So they cannot pass simultaneously through 3 of these balls. They can pass at most through 2 of them. Maybe not even through both, but at most through 2 out of 3. But then they do not know and they do not see what happens inside this third fragment. And for this third fragment, I had 2 possible resolutions, right? So whenever I count these double tangents, it will enter twice. I will count it twice for both resolutions, which I take inside this fragment. But since I count everything with signs, then these will just cancel out, right? And I will get 0. So any double tangent will give me in total 0. I will count it with coefficient which is +1, -1, and then it will give me 0. So the total alternating sum vanishes, right? So if we do manage to find such a rule of signs, excellent, this is very good. Now, all these proofs suffer from one very simple thing, that they lack any construction for these signs. I didn't tell you how to introduce signs for anything complicated, except maybe for the case of double tangents. So how to find such rules of signs? And the whole story here is about configuration spaces and intersections in homology. So let me again explain it on some very simple example. Let me start back from the same idea about double tangents. So suppose I have a pair of immersed curves, right? So I just look at the configuration space of pair of points where there's one point on the first immersed curve, the second point runs over the second curve, right? So topologically, this configuration space is just 2-dimensional torus. It's S1 times S1, nothing more, right? So I will define a map from this configuration space, which is 2-dimensional torus, into a product of 2 circles. How? Well, I just take these 2 points. Okay. So I assume for the moment that these 2 curves do not intersect. So then I connect these 2 points by a vector, and it's a non-zero vector, and I can count a pair of angles between this vector connecting 2 points with tangents to each one of these curves. Right? So here's my map, right? So it's a map from one closed-oriented manifold of dimension 2 to another closed-oriented manifold, actually the same one in this example, of the same dimension. So if so, it has a degree, right? And the degree can be counted by counting, say, preimages of a regular value, counting them with signs, right? So this is exactly the rule of signs which I need. And this local degree, so what is it? So if I would count just preimages of the value 0, 0, these are what? So these are just double tangents of this type, right? So now these vectors look in the opposite directions. Why? Just because of the rule how I computed my angles, right? So it has to be 0, 0 in this case, right? So this is just a double tangent, right? So these double tangents I count with signs, and these signs are the local degree. And the total, we know that it's a locally invariant thing, at least, right? So it's good. So this is just the rule of signs which we need. Now, if instead of this regular value I would take another one, this will give me another type of double tangents, or just take straight angles, then it will count double normals. All these will give me the same because it's the same degree. So in addition to getting some function which behaves nicely, it's locally constant, we have a lot of equalities saying that the number of such double tangent equals to the number of such double tangents, or to the number of double normals, right? So you get for free also a lot of equalities in this way, right? So many other problems which I mentioned before, say conics, tangent ovals, etc., can be treated in the same way. I always say define certain configuration cases, a certain map, and I look at this map and I look at its degree. Okay. Now, this is good, but it's not sufficiently strong. So a much stronger way is just to think about this notion of a degree in the following way. So how should I understand the degree of a map? One of the ways is very simple. I just take the image of my configuration space. If I map it forward to the target, it sits there, and it's a certain 2 cycle, right? And I intersect it with a 0 cycle, 0 dimensional. It's just a point. This intersection number, right? So this is the number of pre-images. I want to understand this as a certain intersection number of 2 things, right? Something of complementary dimensions in the target. So more generally, I can do it in a very similar thing. So I can start from the same configuration space of points where the first point lies on a first immersed curve, the second on the second immersed curve, and I map it not into a pair of circles, but into a triple of points, right? And where each of the factors is the following. I just take the first one will be the tangent vector to the first curve, the second, the tangent vector to the second curve, the third copy is just a vector connecting the points. So double tangent is what? Is a point, is a moment when all these 3 directions are the same. Right? So in other words, it's just exactly the intersection of the image with the diagonal, which lives inside this 3-dimensional torus. So note that this time dimensions of these 2 spaces differ. I map a 2-dimensional torus into 3-dimensional torus. There's no notion of degree, of course. However, I do intersect the image with 1-dimensional submanifold, with the diagonal. This intersection gives me exactly what I need. So, and of course, all this intersection theory tells me that everything is invariant, is well defined. So this is the kind of function which I would like. So exactly the same thing works in high degrees. So you can count. So I gave you here a theorem which is counting of rational cubics, but we have the same theorem for counting rational curves of degree d passing through 3d minus 2 generic points and tangent to an immersed curve. Right, so I just present this simpler version of this theorem because then this number I can exactly describe very explicitly. So it's again some rotation number minus some indices of certain varieties of a special kind, R and Q, whatever. Some nicely defined things. But so for a rational curve of degree d, it would be slightly longer for me to define these R, Q, and P, but basically it's the same thing. So the point is that you can count rational curves of degree d passing through a certain number of points and tangent to something. And note that this is not your standard type of algebraic enumerative problem, because I count tangencies to an immersed curve, so it's a smooth object. Right? It's extremely flexible here. Okay, so it's a nice thing, and you can go up both in degrees of curves. You can go both also in high dimensions. So instead of counting, say, some tangent lines in a plane tangent to some curve, you could just count the number of planes, 2-dimensional planes in R3, which are tangent to an immersed surface. And additionally, you have another thing, so contain a fixed line. And then again, if you count these things with certain reasonable signs, then the answer is extremely nice. So it just depends on the Euler characteristic of the surface and the intersection number of this fixed line with your surface. So it's again the same type of enumerative problem where things are well defined just because you count them with correct signs. So when I write here algebraic number, it means that I count them with signs. And again, the technique is very similar. You can define it using some maps on configuration spaces and some intersections. In homology, you can look at things which are, say, planes which pass through a point tangent to two immersed surfaces, etc., etc. Right? So you can jazz it up. You can also go in high dimensions, and you can introduce some contact structures on symplectic structures and still be very nicely off. So there's a variety of such nice problems which where you look just not at all, say, hypers at such tangent lines, but for example some isotropic lines, etc., etc. Right? So again, there's a number of generalization of this type of things. Good. So now, I actually came to these problems mostly because I was interested in knot theory, and knots can be treated in the same way. So you just think about generic immersions of S1 into R3. Well, of course, then generic immersion is just an embedded, so it is a knot. Or if you take several components, then it's a link. Technically, it's much easier to work with long or string links. It doesn't matter. And you can look at similar problems of intersection and tangency. Right? For example, you can look at quadriseconds. So these will be just lines which intersect a link or a knot in 4 points. And then if you manage to count with these things, again, with certain appropriate signs, then it turns out that you can make sense of all these counting problems very nicely. And just as before, such counting problems, if you manage to produce a nice invariant, then this invariant should be a finite type invariant of a certain degree. Now, how do you count these things? Well, for example, Julia Vero had a problem about counting quadriseconds for a 4-component links, so that this quadrisecond intersect each one of the 4 components in a certain cyclic order. Okay? And then it turns out that if you count them, so she worked in RP3 with these links in RP3, and then there's an answer which is very easily written as certain product or combinations of linking numbers. Okay, so so here I claim another theorem which is very similar. I just look at links in R3, and I will explain you immediately why it's just this linking number. So again, let me just present half of a proof. So suppose that I manage to count these quadriseconds with certain signs. And I just don't tell you what these signs. But suppose that I manage to construct something which will be locally invariant. Right? So then I claim that it has to be this product of linking numbers. Why? Just because it should be a finite type invariant, and it should be finite type invariant of degree less than 3. So it should be degree 2 or 1. Now what are these? These are just the only ones are some linear combinations of such products of linking numbers. Nothing more. Just from the knowledge that it is invariant, I know how can it look like. And then to identify exactly these linear combinations of all these products, I will just take the simplest 4-component link, which is just a pair of hop link. So I link the first 2 components, and then the third and the fourth, right? And then I maybe renumber them some other ways. And what I do is I take two of these very far from the other two. Now, since it's invariant, it does not depend on the local position, so I can pull them apart very far. Now then, what do I count? Well, these are more or less lines which go, if I think about it as a kind of fat point, right, on astronomic scale. This is another fat point on the astronomic scale. Then there should be a line which is just passes through these two points, right, kind of fat points. If I look, just at them being extremely far apart. Okay, so it's a line in a fixed direction. Now let's concentrate on this particular pair. So I count now a line which goes in a fixed direction and intersects both of these components while it's fixed direction. Now this is exactly the linking number. There's nothing more. Okay. So if I would change my problem and instead of 4-component link, look at 3-component links, then if I just again count with appropriate signs of these quadriseconds, will give me what is called Milner's mu invariant, which is the triple linking number, whatever this is. I'll not explain you this. Now, if I do work, say, with a knot, then such quadriseconds, if I look at certain particular ordering here, it turns out to be just the second coefficient of the Alexander polynomial by some reason. And the paper of Budney and Conant, it's quite long with very technical proof, and just the proof takes 12 pages. Just the proof itself. So, and let me just do it immediately without all these complications. So let me again take a configuration space, and I just take the space of 4 points on my knot. I order them just along from this base point, which I think is sitting in infinity because I work with long knot for convenience. Then I just order them in the order of the passage along the knot. Right? 1, 2, 3, 4. Yeah, so it's just configuration space. It's an open simplex, right? Okay, and I just map this open simplex into what? Into a triple of 2 spheres. Now how? I just connect these 2 points, picked up this third and first. Take the direction of this vector. Since it was an open configuration space, so all points are distinct, this is a non-zero vector. Very good. So I just take the direction. It's the first copy of S2. This vector from the first point to the fourth gives me another copy of S2. The third vector from the fourth to the second gives me another copy of S2. Now, my configuration space was 4-dimensional. It's a map into a 6-dimensional space. This space was open. This is a closed manifold. Now, there's obviously no notion of degree. But what I can do is a simple thing. I can look at the diagonal inside these triple of spheres. Right? It's a 2-dimensional manifold. So then, the image of my configuration space, which is 4-dimensional something, will kind of in general intersect the diagonal, which is of complementary dimension. And I can look at this intersection number. Everything is oriented, so there's a notion of oriented intersection number. It turns out that this is exactly V2. So this I can prove kind of almost immediately, but I will not do that. However, note that this configuration space is just an open space. I don't care. I really don't care. I just compactify it really naively without any blow-ups. No problems with blow-ups whatsoever. I just take the close for simplex. And it just turns out that the boundary of this for simplex, after I map it into my product of spheres, it just never intersects the diagonal, even if I do isotopies. Right? So if the boundary of the image does not intersect the diagonal, then this intersection number is an invariant, right? Very good. It is, first of all, it is then a not invariant. It is a finite type invariant of degree at most 2, and I can identify it because we know all finite type invariants of degree 2. Right? And in fact, there's a much nicer way to identify it and to earn a lot of different formulas. And this is if instead of looking at the diagonal, I will say, okay, my intersection number, it's a purely homological creature, right? So I can just homotop this to something which I know kind of something else, right? So instead I can split it, say, into a sum of basic two-dimensional homology classes, right? Because inside of this 6-dimensional space, there are these basic classes which are represented by each copy of this S2. So, and I know that the diagonal is the sum of these 3 classes. And I can just nicely deform it there and intersect the image, not just with the diagonal, but with the sum of these 3 classes, and it will give me some explicit combinatorial formulas for this invariant. Right? So again, this technique, when you work with some intersection numbers, the power is not just that it gives you an invariant, but that you can really calculate it in many ways and earn a lot of nice formulas for that. Right? So maybe just okay. Let me just skip this. So I'll just stop at this point. We have 1 minute more. So maybe I'll just say a few words about this last example with this second coefficient of the Alexander polynomial. So that's the whole powerful machinery of perturbative Chern-Simons, where you work with some kind of standard physical technique of Feynman diagrams, and it tells you how to calculate things. It all makes sense, and there are some configuration spaces and maps which you get in this way. Now, the simplest formula which you get from this perturbative Chern-Simons for this V2, for this lowest invariant, it requires the following. So there are 4 different configuration spaces, some of them of dimension 6, some of them of dimension 4. You should glue together something like 24 copies in total of this configuration space. It's a stratified space, it's not a manifold. You have to do a lot of blow-ups and then glue them along the boundaries which you get when you blow up things. And then you work with the formula, right? So here instead, all my configuration spaces are extremely simple. It's just a 4-dimensional simplex. I don't have to do any blow-ups. I just close it in the most naive way possible into a closed simplex, right? And I just take 1 copy of it and I map it into something. So what's the difference with how is it possible that this is so much simpler? And this is just because I do not care about gluing all boundaries together, because I don't try to define my object as a degree of a map. Instead, I use this intersection theory. I intersect something with a diagonal. And this is much simpler and more powerful than calculating degrees, it turns out. Right? So there's a lot of other similar problems which can be done in a very simple fashion. Yeah.
In your case of the invariants for plane curves, do you have a notion of chord diagrams?
Yes. And they very naturally appear in these maps of configuration spaces, which I kind of use in this technique. They more or less correspond to kind of, they can be encoded by these chord diagrams, basically. So kind of the combinatorics of these maps and spaces is encoded by chord diagrams.
if the invariance for plane curves in, for example, in your example, comes or can be interpreted in the sense of the Vasiljev machinery with the study of the space of immersion.
Of immersion, yeah. Vasily was present when I gave, well, slightly different version of this talk, right? So he said, yes, I think that it can be done, and it's very interesting and something, and and then he started to talk to himself and went to so he left me at least with an impression that yes.
Other question?
And like classical problems like 27 cubics, can you get them on a 27 cubics, 27 lines on a cubic surface? Can you get them somehow from this technique?
Yes, this former student of mine, this Sergei Lanzat, I think that he's done that. I don't know whether he have written it. I didn't kind of follow, but we spoke about that several years ago, and I think that he explained to me that yes, and he was doing all these things, say about tangents to some surfaces, etc. And I think that it all worked very nicely.
In that program, 27 lines, well, the configuration space is really obvious. It's take 2 points there, but the target space. What is the target?
So for the so I didn't tell you how what kind of configuration spaces, targets, and what are the intersections and all these slightly more complicated problems of algebraic geometry. Say when I didn't tell you about this example which I presented before about say rational curves of degree d which pass through such a number of points. In fact, there say when you look at these algebraic curves of degree d which pass through 3d minus 2 points and a tangent to something, then you interpret it in a funny way. You lift your immersed curve to a curve in three-dimensional space of contact elements of the plane, and this whole other configuration of points gives you in some funny way a surface in there, right? And the orientation of this surface is kind of a geometric interpretation of these Welschnger signs. And you look at interpretations of this surface with one-dimensional curve. So it's kind of not totally trivial just to pick correctly the map and the target.